Alright everybody, time for the 10.4 section. This one's going to be about objects known as inscribed angles, and we're going to include a little bit about polygons in this as well. But before we can really start with this, we need to know what inscribed angles are in the first place. So let's start there. An inscribed angle itself is an angle with vertex and endpoints on the circle. So, as an example, let's say that I want to make an angle ABC. Well, remember, B then is the vertex. It's going to be the center of the angle. I'll just make that right here. And I can really make A and C anywhere. I'll make them here and here. So there's A, there's C. So then angle ABC is an example of an intercepted angle. Or an inscribed angle, I mean. And what that means, again, is you'll notice it's starting on the circle, and both of its endpoints, which are A and C, are also on the circle. This should be compared to a central angle, which you learned about last section, which has its vertex at the center and then opens up out there. So this is a new one. The one that I drew in black is the inscribed angle. And then we have the intercepted arc. And what an intercepted arc is, by definition, is the arc between the endpoints of an angle in a circle. So in this case, we have angle ABC. The intercepted arc would be this one right here. It's the one that the angle is sort of enveloping. It's the one the angle is around. So that is the definition of an intercepted arc. We're going to need that. We're going to need that to help us out with this next part. So this is going to help us with a theorem here. The measure of an inscribed angle is, and this is always going to be true, we have that the measure of an inscribed angle is 1/2 the measure of the intercepted arc. So, let's put this into a picture just to make it a little more clear. So let's say that we have this inscribed angle. We can call it kind of like above ABC. So if we have ABC, then angle ABC is going to be equal to 1/2 of arc AC. So if this ended up being something like 30 degrees, then this would end up being something like 60 degrees. And that's how that works. That's how they're related to each other. So looking at this in a few examples, find the measure of BC. Well, here's what we want to do for that one. This 64, so we can see that BA here is a diameter. It's going all the way through the circle. And what that means is that this arc over here is 180 degrees. Now, if that's 180 degrees, what I want you to notice is that ACB is an inscribed angle that has an intercepted arc of this 180 degrees. What that means is that ACB has to be half of 180 degrees, which means that C is a right angle, 90 degrees big. So, if we want to find the measure of angle A, we just do 180 minus 90, which is 90, minus 64, which gives us 26. That's that angle right there. So, now that we know that that's 26, I'm going to clean the picture up a little bit. We know that angle A up there is 26 degrees, but notice that it is an inscribed angle. And here is the intercepted arc, the one that we're looking for. And we know that the angle is half of the size of the arc. So we take 26, multiply it by 2, and we get that this arc is 52 degrees, and that's the measure of BC. Now over in this one, we're asked to find the measure of angle A. So, one thing to notice, we can figure out a few things about this circle right now. For example, since we know that this here is 94, and this is, notice, a central angle, that means that arc CD is also going to be 94 degrees. And we have vertical angles going on, so we know that this angle here is also 94 degrees, which means that this arc is 94 degrees. AOC itself is a diameter. So that means that arc AB and arc BC need to add up to be 180 degrees. So to figure out BC here, all we need to do is do 180 minus 94. That gives us 86 degrees. Then, now that we know that that's 86 degrees, notice that for this angle here, angle A, the one that we're looking for, this 86 is an intercepted arc, which means that that angle is half of that that arc's size, which means 86 divided by 2, 43, is how big angle A is. So, that is how that works. Yeah. So, next theorem then. If two inscribed angles of a circle intercept the same arc, then the two angles are congruent. So what that means is, let's say that we have one intercepted arc that starts out over here and opens up like this. So there's our angle, there's our intercepted arc. If we draw another one that has the same endpoints, but a different vertex, like this, then what that means is that this angle here, the one creating that intercepted arc, has to be the same size as this angle here. Because if they weren't the same size, then they wouldn't be able to have the same endpoints. So, they do have to be congruent, otherwise this whole thing kind of breaks down, doesn't make sense. And we can use that to our advantage. In this problem, we're asked to find the measures of angle A and of angle B. So, let's see what we can notice here then. We know that angle D itself, right here, is 32 degrees, and it's an inscribed angle, which tells us then that the intercepted arc over here is 2 times that amount, which is 64 degrees. We get that from the first theorem that we learned about, the one that was earlier in the page. Notice that A, that angle, is opening up to the same arc. It's also opening up to BC. What that means is that A is going to be the same size as D, which means that A will also be 32 degrees, right there. Now, thinking about B then, we can see that here in the middle, this here that I'm drawing in black right now, is a central angle. since this arc up here is 64 degrees, this is 64 degrees, vertical angles tells us that this one here is 64 degrees, which means that this arc is 64 degrees, arc AD. Let me clean the picture up a little bit before I show the last part of this. So we know that arc AD is 64 degrees. Notice that angle B is opening up to it. Inscribed angle over here, intercepted arc down here of 64 degrees. For that to work, that means that angle B also needs to be 32 degrees. So angle A and angle B were both 32 degrees. And we use sort of a combination of these theorems to help us see that. All right. So a few more terms, a few more examples, and then we will be done with this video. An inscribed polygon is similar to an inscribed angle. Basically, it means a polygon whose vertices are on a circle, and a circumscribed circle is the idea that we have a circle that is surrounding a polygon. So circumscribed circle is the circle that the polygon is inside of. All right. So we have a few theorems that we can do based off of this. One of them is, let's say that we have a right triangle inscribed into a circle. Not a very good drawing on this one, but imagine that there were a right triangle and you knew it was a right triangle inscribed inside. What that would mean then is that the hypotenuse would have to be a diameter. So I knew that it wasn't a good drawing right away because this is supposed to be going through the dead center of the circle, but it's not. The hypotenuse will always be a diameter. If you want to make your drawing better than mine was, please feel free to. If one side of an inscribed triangle is the diameter of the circle, then the angle across from the diameter is right. That's the converse, just the opposite saying of what was there. So that is something that you may find useful throughout all of this. So last one that we have, last theorem, is that a quadrilateral can be inscribed in a circle if and only if opposite angle pairs are supplementary. So if we name these angles A, B, C, and D, this only works if A plus C equals 180 degrees, and B plus D equals 180 degrees. So we will find that useful coming up in the next example. Find the values of x and y. Well, here's what we can do to find x. Notice that x itself is an inscribed angle with this as the intercepted arc. If we find out what the size of km is and divide it by 2, we'll have angle x. So to find km, we just take 80 plus 52, get 132, divide that by 2, and we get 66 degrees for x. So we have that. To find y, we can use the idea that we had in our theorem just above, right up there. We know that this angle and y have to be supplementary for this to actually exist. So we just do 180 minus 114. 180 minus 114 is 66. So y is also 66 degrees. Means that we have an isosceles trapezoid in there. Little throwback to last chapter. And now we have this last problem here. in this problem, it is our goal to find AB. One thing that you should know, and I don't think it printed through very well, is that this is a right triangle here. So add that in. This problem makes more sense. All we have to do then is realize that this angle is an inscribed angle to that arc that we're trying to find. There's the intercepted arc. So if we can find that angle, we just have to double it, and then we'll have our arc sides. So we just do 180 minus 90 minus 28, which gives us 62. To get the arc across from it, we're just going to double that size. So we get that the arc is 124 degrees. And that's it. I'll leave the checkpoint to you if you want a little bit of extra practice before doing the assignment. Thanks for watching. Long video, but tons and tons of information found in it. Last video coming up will be on the equations and graphs of circles. Actually a little bit easier than this section in my opinion. So see you there.